Good morning and welcome back. So, where are we? We're talking about life as defiance. In some ways, for this year's version of the course, I think this is going to be the most important theme for what I want to say. And in order to do that, in order to think about it, we needed to develop a variety of tools. And what's interesting is some of those tools actually have the sniff of equilibrium physics, and yet they're still very useful. And so, what we're going to do today in this particular vignette is to talk about truly one of the most remarkable ideas in all of physics, which is the chemical potential. And just to give a little bit of background, I want to comment on probably America's greatest ever American-born scientist, and that's Josiah Willard Gibbs. So Gibbs was a professor at Yale University. It's an interesting biography. He, as a youngster, did the equivalent of a postdoc where he went off to Europe and he was in Heidelberg and I forgot where else, but he got to hang out with people like Kirchhoff and Helmholtz and others. And then he basically went back quietly to New Haven, and at first Yale didn't even pay him, and he conducted himself incredibly creatively, I guess I would say. And he wrote a very few papers. He wrote something on the order of 20 papers total in his life. And one of the most important of all is this long tome, which is published in the Transactions of the Connecticut Academy of Sciences, called On the Equilibrium of Heterogeneous Substances. And the reason that I feel that this is so important is some of you might remember a several versions of the second law of thermodynamics, which are verbal. For example, you can't have an uncompensated transfer of heat from a cold source to a hot source without something else happening. That's the kinds of words we hear. There's a Clausius statement of the second law, and there's a Kelvin Planck version, and so on. And for me, when we do physics, it's nice to be able to state our thinking mathematically. And here, as I say on the right-hand side, what Gibbs did is he basically had this insight that equilibrium can be thought of as one idea only, and it's a mathematical idea, which is if you have a system, you remove a constraint, you ask what's going to happen to that system. The answer is it is going to evolve until it has a maximum in its entropy, and then it will stop. And that is the privileged terminal state that we know of as equilibrium. It's truly awesome, and I think that we take it for granted all the different senses in which we get away with that as the way we think about problems, whether it's the equilibrium occupancy of hemoglobin molecules. Let me take a deep breath. So, what I do is I take in oxygen into my lungs, I increase the partial pressure of oxygen. That has the effect of saturating my hemoglobin molecules. They go out of my blood, they dump the oxygen, so on. Another totally different example, which we already did, was we could imagine quasi-static loading of a polymer like DNA, and in that quasi-static loading, at every instant, basically the DNA is if you like, the total world is in its entropy maximum state. And part of the reason that I wanted to bring all this up is that this section of his paper called Criteria of Equilibrium and Stability is where he introduces the mathematics of using reservoirs of different types, and the virtue of those reservoirs, they allow us to turn an entropy maximization problem of system plus reservoir into a free energy minimization problem of just system. So let's contemplate an Eppendorf tube. I have something in it, I put it in the Pacific Ocean, and I have the tube closed. And so that is a fixed temperature and fixed volume ensemble, if you let me use those words. It's really a fixed temperature and volume reservoir. And now, if I am interested in what happens inside of that Eppendorf tube, I need only minimize the free energy. But I should not forget in the back of my mind that really what I'm doing is maximizing the entropy of the composite system of Eppendorf tube plus ocean. That's actually what's going on, is that that net system is reaching a state of maximum entropy. What is that state of maximum entropy? It's when the temperature of the material inside of the Eppendorf tube is the same as that of the ocean. That's the maximum entropy state. Now, we can do that without referencing the ocean. We can not think about the entropy of the ocean and strictly focus on just quantities associated with the Eppendorf tube, and in so doing, what we do is we minimize that free energy. Anyway, why do I bring it up? Because Gibbs, he really nailed, if you like, the question of mass transport and chemical transformation. He was able to say the conditions under which you would have a spontaneous change of a system that corresponded to a chemical reaction. And the language for doing that was this incredibly powerful concept of the chemical potential. And, I think it's interesting for us to understand how scientific concepts become part of our everyday vernacular. Because I can ask you a question. You can see I'm wearing a sweatshirt right now. I can ask you the question, hey, what's the temperature like? Or alternatively, I can say, when I'm in an airplane, I can say, oh man, my ears are hurting. Or when I dive down in the water, I can tell you, oh man, I was diving and my ears started to hurt because the pressure was high. But we don't, in our everyday discussion, I would never say to you, hey, how are you finding the chemical potential today? And the pity of that is that the chemical potential has equal status to temperature and pressure as a thermodynamic variable. And in my opinion, we kind of get ripped off in our physics education because T and P have sort of a more prominent position, whereas in fact the more interesting one, to my mind, is the chemical potential. It's a subjective statement. We're each allowed to have our own subjective tastes. I don't like avocados. I don't like mushrooms. I love the chemical potential. I think it's stunningly powerful. So here's what Gibbs said. I've already assigned this as a homework for the students. What Gibbs said is that if I have this composite system, let's look at this one first. So I have a composite system of two separate partitioned regions where I have a gas inside. There's this partition. The brakes are on, and I release the brakes. And what will happen is that this partition will move, and it will move in such a way that the entropy gets maximized. And that entropy maximum corresponds to equilibrium of pressure. In the top case, when I allow for this partition to transfer energy, then what I find is that that corresponds to equality of temperature. And for this case of interest, what we find is equality of chemical potential. And I think I want to actually have a go at explaining that. So let me add a page here, and let's do the calculation to see that. So here's the idea. So the idea is that the total entropy is equal to the entropy of the particles on the left-hand side plus the entropy of the particles on the right-hand side. And what do I mean by that? What I mean is that if particles get transferred, then you know that the S equals K log W, the microscopic multiplicity, will change when I move particles from one side to the other. And so Gibbs says, well, I have a condition, which is that ds tot is greater than or equal to 0. What do I mean by that? That what we will see over time is that the system will continue to evolve. It will continue to increase its entropy until it reaches the maximum, at which time this inequality becomes inequality and it's equal to 0. Let's write the derivative. So I can write that as ds1 by dn1, dn1 plus partial derivative of the entropy of the right-hand side with respect to n2, dn2. But I know that there's this constraint. So I have a constraint, and that constraint is that n1 plus n2 is equal to n tot, which tells me that dn1 is minus dn2. Whenever I increase n1, I have to have decreased n2. We can use that constraint up here, and that implies ds1 by dn1 minus ds2 by dn2, all multiplied by dn1, and that's greater than or equal to 0. Comment, and this is, for the moment, this is just a definition, and it's not I find it's not as intuitive a definition as the one I'm about to show you, but a definition of the chemical potential is that mu over t is equal to minus ds by dn. So if I substitute that in up here, what I find that this implies is mu2 minus mu1 dn1 is greater than or equal to 0 in any spontaneous process. So let's check it out. If mu2, the chemical potential on the right-hand side, is higher than that on the left side, then mu2 minus mu1 will be positive. Since it has to be true that the term in brackets times dn1 is greater than or equal to 0, that means that dn1 is positive. That means that stuff is flowing from right to left. And so the number of particles in the 2 reservoir will decrease, the number in the right reservoir will increase. So the mu is a driving force for mass transport. And more generally, mu is a driving force for mass conversion. Like when we have ATP goes to ADP plus inorganic phosphate, that reaction, we can tell what the direction of spontaneous reaction will be based on the current chemical potentials of ATP, ADP, and phosphate. And we'll come back to that. So, this graph I'm not going to talk about in any detail, but what we see is the entropy of the right-hand side. So on the bottom, the x-axis here is number of particles on the left. So if there are no particles on the left-hand side, that means all the particles are on the right-hand side. And so the entropy is at its maximum. And as we start to take particles out of the right-hand side and putting them on the number of particles on the left side, L tote. So this curve, the red curve, is the entropy of the left-hand side. There's no particles over here in the left-hand side, and that means that so that corresponds to over here, and this point corresponds to over here. So what happens is we add particles to the left-hand side, its entropy goes up. As we add particles to the left-hand side, the right-hand side's entropy goes down. At some point in the middle, at some point, if the volume of the two sides is equal, it is in fact at the middle, then the entropy will be maximized. And this is the terminal privileged state. It's the entropy maximizer, and that's what this calculation that we just did is all about. Okay, so what I want to do is I basically want to work out for you a formula for the chemical potential. So in this particular vignette, I'm not yet demonstrating the incredible power of the chemical potential. For the moment, I'm doing a technical detail, which is computing it, showing how for a gas or solution of non-interacting particles, what that chemical potential is. So what we're going to do is we're going to compute the chemical potential for what I'm going to call an ideal solution. So I have these red particles, they're in water, for example, and I want to figure out what their chemical potential is. So the definition that I'm going to use is that it's the free energy of the system when there's n plus 1 particles minus the free energy when there's n particles. I'm measuring how much the free energy of the system changes when I remove one particle from it. And I can rewrite this as u of n plus 1 minus t of s, t times s of n plus 1, and then minus u of n, and then plus t s of n. So that's what I mean by this definition. So I'm using the fact that the Helmholtz free energy is given by u minus ts, and I'm just doing the before and after. So that's what's involved here. So let's see here. Oops, I added the page. Sorry, I'm just trying to add a page so I can do my calculation. A little weird. Okay, I don't know if I succeeded in adding a page in the right place. Man, this is annoying. Okay, so what is U of n? So U of n is equal to n times epsilon solution. What do I mean by that? What I mean is that each one of these particles, each one of these molecules, has a certain energy when it is stuck in solution. Imagine a lipid molecule, a single lipid molecule in water. So you could think of that epsilon solution as being the energy that we attribute to the fact that the tetrahedral bonding of the water has been disturbed by the presence of that single lipid. And so in statistical mechanics jargon or framework, what we do is we assign an energy to that. It's actually a free energy, and we're never going to calculate it. We don't need to know it. We just give it a name, which is epsilon solution. So that tells me that un plus 1 minus un is equal to n plus 1 epsilon solution minus n epsilon solution, which is equal to epsilon solution. So that's the contribution of the energy to the chemical potential. Now we need to do the entropy part. So S of n plus 1 minus S of n is given by Kb log of Wn plus 1 minus Kb log of W of n, which is Kb log of Wn plus 1 over Wn. What is this W? Remember that W of n is omega to the n power over n factorial, omega minus n factorial. And this is the number of ways of putting n ligands onto the omega lattice. So let's go back up to our picture just so it's clear what I'm talking about. So here there are omega lattices, and there are n plus 1 ligands. So that's what my notation means. So given that, then I have that S of n plus 1 minus S of n is equal to Kb log, and then omega to the n plus 1 power over n plus 1 factorial times omega minus n plus 1. Oops. I'm mixing up my metaphors here. Please forgive me. So this was an omega factorial. I made a mistake because I got ahead of myself. So please let's regroup. I was saying nonsense. Okay, this is the correct Wn, the full and complete omega choose n. But as I've said earlier in the course, this can be rewritten as omega to the n power over n factorial. How do I know that? Because in the this is for omega much greater than n. And the way I like to think of this is that if I go to the Rose Bowl, which is a stadium that has like 60,000 seats, and I go there with 10 students, then the number of choices for student 1 as to where to sit is 60,000. The number of choices for students 2 is 60,000 minus 1 possible seats, but we just call it 60,000. And we're not worried about the fact that when we choose random number out of 60,000, that 2 students are going to end up in the same seat. We're not worried about that. So that approximation is what I've written here. So now I can compute Wn plus 1 over Wn. That's equal to omega to the n plus 1 power over n plus 1 factorial times, now I have n factorial over omega to the n, and this ends up being equal to omega over n plus 1, which is approximately equal to omega over n, because omega is of order something like let's say a billion, and even in E. coli, a typical number of proteins that I have wandering around is, like 10 or 100 for transcription factors. Even the most abundant molecules, like a tRNA, a given species of tRNA is going to come in at like 30,000 copies. So 30,000 over a billion is a small number, so we can get away with this approximation. So what we see is that S of n plus 1 minus S of n is equal to kb log of omega over n. So now we're ready to go back to our mu, which is fn plus 1 minus fn, which is equal to delta u minus t delta s. That leaves us epsilon solution minus kbt log of omega over n, which I can rewrite as epsilon solution plus kbt log of n over omega. And we're almost there, because now if I think about this picture, this volume, so let me shade it, this little volume, let's see here, this little volume, little v, that's the volume per lattice site. So let's clean this up by multiplying. I can always multiply by 1, right? So I can rewrite this as epsilon solution plus kbt log, and then I have n over omega v times 1 over 1 over v, which leaves me with epsilon solution plus kbt log c over c naught, where c naught is the standard state concentration and it's equal to 1 per lattice site. So that corresponds to this very interesting choice of concentration, where I have a ligand on every single lattice site. So this is C naught. C naught is that concentration. Okay, so we're done. And we're done with a technical point. We found that mu for an ideal solution, the chemical potential for an ideal solution, is given by epsilon solution, which is bare energy, plus kBt log of C over C naught, where C is the concentration at which the solution finds itself. Okay, this may all seem rather abstract, but note that here we saw that the chemical potential difference is the driving force. And what we've now got is an expression for the chemical potential, which is this very important result right here. Okay, so we're going to, in subsequent vignettes, we're going to use this result for the chemical potential quite a few times, as you'll see. We'll find it quite useful for lots of different contexts.